The recording. Perfect. Thank you. Okay. Well, welcome everyone. We're very excited to have you here. This Rubin Science Assembly is one and a part of our science preparation seminar series. And today we're going to be focusing on solar system science. So just to quickly go through the agenda, we're going to start with a few announcements, and then I have a short presentation just to talk about some of the expected advances that LSST will bring for solar system science, and I'll also go over the LSST data products that are going to be relevant to solar system science. And then I'm going to hand things over to my co-host, Erin Meisner, who's going to give us a hands-on tutorial walking us through the simulated data sets of solar system objects that are currently available on the Rubin Science platform. And you'll be able to either follow along with those tutorials or you can just watch. And then at the end, we'll have some time for questions. Okay, so first, if you are new here, uh, oh, thank you, Erin. Erin also has the link to the slides in the chat as well. There's a lot of links and helpful information in these slides. So if you would like to follow along or have access to any of the links in the slides, the link has now been shared in the chat. So if you're new here, welcome, first of all. One of the really great things for you to be able to do if you are new and you have not done yet so far is to get an account on the Rubin Science platform. You can go to rsp.lsst.io and there are instructions there on how to set up an account if you don't have one yet. It is the place where all of the Rubin data, analysis tools, computational resources, all of that is going to be available on the Rubin Science platform. So if you want to do science with Rubin data, it's important to get an account so that you will be able to do that. Currently, we have simulated data sets available on the Rubin Science platform. Right now, we have data preview 0 or DP0, and there's a number of links on this slide to various parts of DP0 and information about that preview data set. The one that's important for this group is DP 0.3, which is focused on solar system objects. There's also a lot of other information on this slide. The one thing I will point out that's a really great resource is the community forum at community.lsst.org. This is a great place if you have a question once you start playing around with a preview data set or real data down the road to ask questions, to get help. There's also an archive of all of the questions that people in the community have asked previously, and all of the answers and responses they received are also all on there. So it's a really great resource if you're running into any issues to go look for answers to your questions or post your own question if you can't find the information that you need on there already. Okay, so there's also a number of upcoming events. The Rubin Community Workshop is coming up at the end of July and early August in Tucson. Registration and abstract submission are currently open. And in fact, both the abstract submission deadline and the deadline for submitting breakout session proposals is tomorrow on April 25th. So if you haven't submitted an abstract or a proposal for a breakout session for the Rubin Community Workshop and you would like to, please make sure that you do so before the deadline tomorrow. As I mentioned at the start, this is also one in a series. We're calling these our science preparation seminars for the Rubin Science Assemblies at the moment. We've been having these since the middle of March. This is the second to last one. So next week is the last one that will be happening on May 1st, and it's going to be covering stars and the Milky Way. There's also a Rubin Users Committee meeting and listening session coming up on Monday, April 28th. And if you're interested, you can find information about that in the link to the community forum post here on this slide. And also, there is an open call for input on community filters for the Antares broker, where that input is due at the end of May. And if you're interested in that, there's also information in the forum post link on this slide as well. So we encourage you to check out all of these different events and information as well. Okay, we also can't have announcements without also mentioning that we've officially achieved first photon with the Rubin Observatory, which is very exciting. The engineering test phase of the Rubin Observatory with LSST CAM officially started last Tuesday on April 15th. There's a lot of information on the slide I don't have time to go over, but it all comes from the post on the community forum, where there's the link at the top of the slide here. Um, that is just updating the community on how things went. It's been going very well so far. And now the big priority is really just commissioning the entire system to make sure that it's running automatically and reliably. And there will be updates posted to the community forum roughly weekly, as was done with the ComCam commissioning campaign. That's also going to be happening now for LSST CAM commissioning as well. So we encourage you to keep an eye out for those updates that will be coming as we're going through this next exciting phase of the project. Okay, we also want to remind everyone that Link Frameworks has office hours on most Thursdays at 10 a.m. Pacific. There's lots of information in the slide, including the Zoom link to those office hours as well. And if you have feedback about the Rubin data products or the Rubin science platform, the Rubin Users Committee would love to hear that feedback. And there's a lot of information on this slide about how to be able to contact them to give them that feedback. Okay, so that's the end of all of the announcements. There's a lot going on. It's a really exciting time for Rubin right now. So let's now move into the science part of this seminar. So for solar system science, the Rubin Observatory is going to be fantastic for discovering small bodies across the solar system. I probably don't need to really go through all of these populations for this audience, but just to kind of drive home the point, these small body populations are going to range from things in the inner solar system with near-Earth objects and main belt asteroids. We'll lump the Jupiter Trojans and the short period comets, including Jupiter family comets, in with those. Then moving more to the outer solar system in the giant planet region, we have the centaurs. Beyond Neptune are the trans-Neptunian objects, getting into the dwarf planets, extending out to the distant solar system, where you also have long period comets and Oort cloud comets and many more populations all mixed in there as well. But there's small body populations ranging across the solar system. And one of the most important things about these small body populations is what information they hold about how our solar system formed, how planets and all of these small bodies themselves formed long ago, and how our solar system has evolved and changed over time. All of that information is imprinted on the orbital distributions of these small body populations, as well as the physical properties of all of these bodies as well. So LSST is really going to help us find a huge number of these and really help us to better understand the history of our solar system. So looking on the right-hand side here, this is a fairly recent simulation of the LSST observing strategy, showing the color scheme here is the number of observations expected on different parts of the southern sky at the end of the 10-year LSST survey. And you can see here, so on the left, you can see where the ecliptic plane goes across the sky here in these equatorial coordinates. And so this purple bump on the left on your right plot here that's labeled with NES is the North Ecliptic Spur. And so you can see that we're going to have really nice coverage of the entire ecliptic plane with many hundreds of observations being taken across the ecliptic plane through the 10-year-long survey. So LSST is going to be have very wide coverage for finding a lot of these different small bodies, and it's going to be very deep and go very faint. So we're going to be able to find many more than we've been able to find so far. In addition, one of the hardest parts of the solar system to see are things that live very close to the sun. So LSST is also going to be including a microsurvey that will use up to 3% of the observing time to enable discovery of small bodies that live at low solar elongations near the sun that are really only visible during twilight hours. So when talking about how many solar system small bodies LSST is expected to find, I think these are somewhat outdated numbers. There are new numbers that are going to be coming out very soon, but I think most of these are pretty consistent still. But you can see that LSST is expected to find more than 5 million new small bodies in the solar system. We currently know of about 1.5 million or so, and so 5 million is going to be a huge increase in the number of discoveries. And all of these small bodies are going to be well characterized with their orbits and light curves and absolute magnitude estimates by hundreds of observations for each and every one of these objects. The discovery rate for these small bodies in the solar system is heavily skewed toward early on in the survey, with something like 80% of all of the small body discoveries expected in the first 3 years alone of the 10-year survey. And you can see from the plot on the right that even by the end of the third week of the LSST survey, that we expect LSST to be discovering something like 70,000 new small bodies on a nightly basis. So every night we expect LSST to be detecting millions of small bodies in the solar system, and many tens of thousands of those are going to be brand new discoveries. So right off the bat, LSST is going to be enabling significant small body science. And that's coming very soon. So it's a really exciting time coming up here. LSST is expected, as I said, to catalog over 5 million small bodies in its 10-year lifetime through hundreds of observations and multiple band passes for each of these objects. The magnitude range it's going to cover in R band goes from roughly 16 to 24 and a half, and that on-sky footprint covers 18,000 square degrees in the Wide Fast Deep survey, which is the main portion of the survey. Solar System Processing and the Minor Planet Center will link all of the solar system detections into orbits, and they'll provide metadata on the observing conditions from those detections as well. So some of the basic capabilities that LSST itself is going to provide are orbital distributions for small body populations, multi-band photometry for individual objects, sparse light curves, photometric variability, PSF source measurements, image cutout tools that will allow you to look for brightening events or cometary activity. In the nightly alert stream, there will also be measures of source extendedness included that will indicate whether something might be undergoing a disruption event or has cometary-like activity as well. So a whole host of information about these small body detections and discoveries are going to be produced by LSST itself, in addition to just discovering all of these objects. There is also a solar system science collaboration. Any Rubin data rights holders who are active in solar system and planetary science are welcome to join. There's a link to the website here. It's a very active collaboration, lots of work being done to prepare for all of this great science. We've also been very active in participating in decisions such as optimizing the survey cadence, things that will affect our science, making sure that our science, as well as everyone else's, is all still going to be prioritized in whatever final decisions happen for the survey. So if you are interested in joining, I'm a member. We would love to have you join as well. Okay, so let's move into some of the LSST data products. So the Rubin Data Management has been building the LSST science pipelines to include multiple things, or to do several things. It'll process all of the images from LSST, detect and measure sources, and maybe most importantly, deliver science-ready data products. So today's focus is going to be on those data products that are really relevant to moving objects in the solar system. So there are three types of data products. The first are the nightly alerts that will come out within 60 seconds of the end of a visit acquisition. So within those 60 seconds, the raw images will be processed, a template will be subtracted, and the difference image sources will be detected, associated, characterized, and then they're going to be distributed to these community brokers as these nightly alerts, where users will be able to then start rapidly analyzing them and see what's happening with these detections as they're happening in near real time. So for the solar system, this is going to include measurements of all of the detections on these difference images that include both known and unknown solar system objects. So we'll have 10 milliarc second astrometric precision and 10 millimeg photometric precision, and a bunch of other information will come out in these alerts as well, that will allow you to know when something is trailed, or if a known object has activity or something like that. The second data product come out on a daily basis. So these are the prompt products database, or for solar system, we're calling them the daily data products. So these are updated on a daily basis with all of the new difference image analysis, or DIA, data products. So for the solar system, this includes catalogs of orbits and physical properties that will be updated on a daily basis. So the orbit solutions and designations will come from the Minor Planet Center, while the physical properties, such as absolute magnitudes, extendedness, all that kind of stuff, will come from LSST itself. It will be computed in the LSST data and made available in these catalogs. There are 4 different catalogs that will be coming out in these daily data products for LSST. I don't have time to go through what all of these are, but they're going to include things like the 5 sigma detections, and the per sky observation quantities for each of these, as well as all of the orbital information that comes out of the MPC. So if you would like to know more about what is in these catalogs or the schema that are in these catalogs, all of that is available on the DP 0.3 website. So we encourage you to go look at all of the greater detail there. Also, eventually, all of the raw and processed single visit images, as well as the difference images and the difference image templates, will be available for download about 24 hours after the end of each visit acquisition as well. So those images will eventually be available in addition. The last data product are the yearly data releases that will include the difference image analysis, co-added images, and a reprocessing of the catalogs that have all of the data to date. So again, for solar system, this is basically going to be a reprocessing of those 4 catalogs so that we essentially have a gold version of the daily catalog is what will be coming out in the data releases, in addition to a special LSST only catalog of all of the solar system objects discovered by LSST, that can be used for things like population studies. And one final note, both the prompt or daily and annual data release data products, all of that will be available for users to have access to analyze on the Rubin Science platform. So we really encourage you, if you haven't done so yet, to get an account on the RSP. Currently, we have the data preview 0.3 website here, simulated data set here. There's no images right now for solar system objects, but we do have these 4 simulated catalogs. And here's a link to that DP 0.3 website where you can find all kinds of information. Some of the information I don't have time to go over are the daily data products, how these daily data products are produced, as well as how the solar system processing pipeline works. So this infographic, along with a larger text description for how this pipeline and these data products works, can be found at the DP 0.3 website, as well as information about how tracklet linking and orbit fitting will actually work as well within the solar system processing pipeline. So again, if you would like to know more information about all of this, we encourage you to go to the DP 0.3 website and check out all this information. Okay, so very quickly, in my last couple of minutes, I wanted to talk about the timeline for all of this upcoming data coming out. When does everybody get a chance to actually start playing around with not just the simulated data, but real data? So this is where Rubin's early science program comes in. And the goal of this program is to provide early access to the data products and the services that are needed to produce high impact science from the time starting with commissioning up to and through the first data release. So as I've talked about, we already have this DP0 simulated data set available now on the Rubin Science platform. In June or July, after system first light events, the media events happen, data preview 1 will be released, and it will include data from commissioning of ComCam. Then we have DP2, which has data from the LSST science camera or LSST cam commissioning, and that's expected to be coming May of next year. And then we have data release 1 that's anticipated in January of 2027. In addition, the alert stream will be continuously scaled up, starting with commissioning all the way through the first year of the full LSST survey. And all of this is going to be available on the Rubin Science platform. The data, the analysis tools, computational resources, all of that is accessible via the Rubin Science platform. So again, please get an account if you don't have one already, especially soon, because once the data starts flowing, we're going to get a backlog of people wanting to get accounts. And so getting it early is definitely encouraged. What's going to be in all of these different data previews and data releases? You can find all that information in Rubin TechNote 11 or RTN 11, and I'm going to show you how to find this TechNote on the next slide. But there's a really nice table, table 1 in this TechNote, that explains what of the different data products are going to be made available in these different data previews and data releases. So right now we have DP 0.3 that has just the simulated catalogs of solar system objects. DP1 is the next thing that will be coming out. Currently, there are no plans for solar system objects to be in DP1. We're hopeful that by DP2, with the LSST CAM science validation data, that we will have solar system objects. However, on this last slide here that I have, this is how to access this Rubin TechNote 11, RTN 11. And I want to point out that this TechNote is continuously updated with what is going to be made available through this early science program in these different releases that are coming out, both the data previews and the full data releases later. So as we are going through all of the commissioning data, and we're trying to figure out what is in there, what we can actually pull out and provide to the community, this is being updated on a regular basis. So if you go to this page, you can see on the very front of the document, there's a last revision date. You can see if that's recently been updated since you last looked. There might be some new information in here. So we encourage you to check this out, but also check back continuously, because it's possible there could be more information, and there could be some surprises that come out where plans change as we're getting to look more at the data. So we're trying to get everything that we can ready to go for all of you to be able to do all of this great science with the data that we have available for you. Okay, so I know that was a lot of information. I talked really fast and crammed a lot in to the last 20 minutes or so. I think before we go on to the hands-on tutorial and I hand things off to Erin, maybe we have time for questions if anybody has a short question about anything that I've mentioned so far that they want to ask. Yes, Bob.
So the solar system objects will be rotating. Each image will be at different distances. Will there be any way to do coeds on solar system objects of interest?
I mean, the solar system objects, I think, should be in the co-added images. I don't think they would be taken out, but knowing where they are, they won't necessarily be identified easily in the co-added images. All of the difference images, as you said, will have observations of objects taken at different phases as they're going around their orbits, different distances, different rotations. So there will be some sparse light curve information for all of the objects as well. As far as trying to add things together, I don't know if there are actual plans. Maybe someone else here knows whether.
I
Well,
can.
sorry, go ahead.
There will be tools that users will be able to use to provide a path through the sky as a function of time, and then you can look for images that would correspond to those points in space-time and coed them. But of course, because the phase space is huge, it will not be done automatically for everything. But you can do, if you have a special object, you can do that. In co-edited images, you are unlikely to see any moving objects because everything that is not repeated at the same spot on the sky will be flagged out. It will be filtered out. So you will not see them in co-eds. But you will have light curves. And as far as I remember, there will be also a model that will give you, at the very least, phase angle and then the best estimate of how you should correct the observation to put all the observations on that hypothetical 1 AU from Sun and Earth, the standard calculation of the absolute magnitude for asteroids. And if you want to learn gory detail, then the best document to start is data products definition document, which is, I'll put in chat. I'll put short link in chat.
Great. Thank you, Jocko. Okay. Thanks for the question, Bob. I think at this point, we want to move on to the hands-on portion of the seminar so that we don't run out of time for that. So I'm going to hand things over to Aaron.
Okay. Thanks, Sarah, for the great overview. Yeah, so we have two hands-on demos today. One is a notebook demo, one is a portal demo. Both use data preview 0.3, DP 0.3, our current solar system data preview that's being served at the Rubin Science Platform RSP. In the notebook tutorial, we'll sort of focus on overviewing some of these key tables for the solar system that Sarah mentioned, with an emphasis on the main belt. And then in the portal tutorial, we'll focus on looking at the population of trans-Neptunian objects, TNOs. Next slide, please. So this is a slide with some detailed instructions for how to actually get access to the notebook that we're going to run today. And in detail, I think actually what I'll do from here is probably take over the screen share and just show how to do this visually rather than try to read you every word on this slide. And I will also paste into the chat just the git clone command that you would use to get the specific notebook, since that's kind of the most one of the most important parts that would be hard to copy and paste or read off that slide. So let me begin screen share. Hopefully folks can see my screen. We'll start off by going to data.lsst.cloud. We're going to do the notebook demo first. So I'm already actually logged in, so I won't do every step in detail here for you, but you would click on this big notebooks panel right in the middle to get started. And then from there, you would select the recommended weekly image, the version of the LSST pipelines basically to use, which I believe is weekly 2025-09. And for this week, we would want the medium size container. So again, since I'm already logged in, I won't show that. But once you go through those couple steps, then you arrive in the notebook aspect. And from there, we would go to this plus sign and make a new terminal window. And we'll start out in the home directory, I believe. So there's not really any need to move, or actually maybe not. Let's go to the home directory and we'll run our git clone command, the one I just posted in the chat there in Zoom. And this will bring in the whole repo of the science preparation seminar series that we're running here. We only want one of these though. So once you've done that, we'll go to home and you'll find the directory that we just cloned. That's DP1 SciPrep Seminar. So we'll go there. Then we'll drill down into the solar system subdirectory and we'll open up the IPython notebook, Jupyter notebook file here and get started. Okay, right. So today's demo is just about sort of exploring the overall tables that Sarah mentioned, with also a little bit of emphasis on the main belt. I'll just skip to the parts that we actually do hands-on and explain as we go. So the first thing we do in Rubin LSST Jupyter Notebook demos and tutorials is always to set up the basic environment and so forth. So that starts with package imports. Some of these are standard Python stuff that you'd almost always use, like NumPy and Matplotlib. But one key one here that's LSST specific is from lsst.rsp, import git tap service. This is what allows us to make actual queries to the DP 0.3 tables on RSP. So let's run that to get our imports. Also, as a matter of best practices, we define functions and parameters early on. So there's only one function we define for this quick demo, and that is to calculate the semi-major axis from the perihelion distance and the eccentricity, because those two parameters are natively in the tables as columns for DP 0.3, but not the semi-major axis. It's just this one quick line of math. So let's define that function. Now, the next thing we're going to do in order to be able to query, explore any of these tables is to make a tap service client. And so that basically involves instantiating a service object using the get tap service function that we just imported. And importantly, you have the argument to this get tap service function is SSO tap for the DP0.3 solar system tables, whereas for DP0.2, that would not be SSO tap, it would just be tap. So let's create our tap service object here by running this cell. And so the first table we're going to look at real quickly here is called MPC orb. For DP0.3, MPC orb is basically like a truth table of all the simulated objects. Some of them are real and some of them have made up orbital parameters. There's something like 15 million of them total, as we'll see. And so MPC orb is basically telling us the orbital parameters of all the objects that went into the Rubin observational simulations of DP0.3, some of which are detected in the simulated observations, some of which aren't. And for the real MPC orb table, this will have real orbital elements computed from the MPC and stored by Rubin. So that's a little bit of a difference here with the simulated data set, that in this case, the MPC orb table is sort of like a truth table of the true orbital elements. So let's start off with a relatively simple query, just a select count query to count the total number of rows in MPC orb table. One thing you'll notice here is that there's this DP03 catalogs underscore tenure part of the query that is referred to as the table collection. And the underscore tenure means we're using the table collection that has the sort of full 10-year simulation of LSST observations for DP0.3. There's also a smaller 1-year version that only simulates the first year, but we won't use that here. We'll use the 10-year throughout in this case. So let's run our query to just count how many rows there are in the MPC orb table. Let that run for a second, and indeed we find there's something like 14.5 million rows. So, the current number of known solar system objects is on order of 1 million. As Sarah mentioned, that'll increase by a big factor for LSST. And then since this is sort of like a parent sample, which could have maybe distant or very faint or very small objects in it that aren't detected, you get to this big number around 14.5 million here. So one nice thing when we're getting started out, in order to just get a feel for what we have to work with, is that there's this sort of meta tables available in DP0.3. So there's this tab schema table collection, one of which is the table tab schema.columns. And so we can start out by querying that to just get a list of the column names that are in this 10-year MPC orb table. That'll just give us a feel for what we have to work with once we start actually querying it. So let's run this table of the tab schema.columns table and print out the results. And indeed, you can see that there are various columns listed here, and they nicely have the name, the description, and the unit. So you can see, as I mentioned before, eccentricity is included here, E, inclination, MPCH, the H band, the H absolute magnitude for each solar system object, which is kind of like a proxy for its size, and so on and so forth. I won't read all of them, but we'll use a few of them in the later queries in this notebook demo. So let's start out by now actually making a query of the MPC orb table now that we have a sense of what the columns are. We'll start out for simplicity by just selecting all the columns, although in a real science case, you would probably want to put some effort into optimizing exactly what columns you pull out. And because this is such a big table, as we found, more than 14 million rows, we're going to want to take an approach to trim that down and basically get only 1% of the rows. I won't go into full detail here, but the SS object ID column, which is available, is kind of like a uniformly distributed integer. And so by restricting to about 1% of the range of that integer, you can get a roughly 1% random sample of the catalog. So that's what we're going to do in our query. We're querying on SS object ID between these two numbers, which we know encapsulate about 1% of the total range of SS object ID. And now we're going to actually run this query. So here's what this looks like. You call the submit job method on the tap service object we instantiated before using a query that we just defined as the input parameter. So let's run this. It may take up to a few dozen seconds to run, I believe. Then there's a few other lines here about, job.run to actually run the job and to wait for the job to actually finish. And a sort of good practice to do is to always take the raw results object that's returned and cast it immediately to a pandas data frame, just sort of for ease of use. So that's what's seen in the next line there, is that the first thing we do is we take the result and we turn it into a pandas data frame. So I'll run that in a moment once this query finished running. There we go. Yeah, good to see that it's running at a similar speed when all of us are running it at the same time. That bodes well. We've just casted this to a pandas data frame, and let's look at the length of the data frame, the number of rows. Indeed, it's about 144,000, which is about 1% of the total size of the table, which is great. A statistically valid size, but not too huge to work with. So the first thing we're going to do is just make some simple histograms of columns that are natively provided in the MPC orb table. So we're not going to do any derivation of additional columns or do any math to derive new quantities. We're just going to plot things like eccentricity and so forth that are directly available in the table. So let's run that now. I won't explain all the subplots, but you can see that, for example, the eccentricity subplot, these are histograms, 1D histograms. In some cases, they have log y-axis. So you can see that the eccentricity, it tends to cluster towards low values, i.e. things tend to have relatively circular-ish orbits. Inclination, it similarly tends to bunch up towards low values, i.e. things seem to be pretty much mostly, relatively speaking, in the plane of the solar system, and so on and so forth. So that's a good sort of initial look at some of the MPC orb columns. Now, I wanted to talk for a moment about the SS object table. That's another different table that's very important for the solar system from LSST. SS object you can think of as kind of similar to MPC orb because it has, again, one row per object. But a main difference is that SS object only has objects in it that were actually detected, or in this case, actually detected in the simulated DP0.3 survey. So it'll be a subset of all the 14.5 million rows in MPC orb in this case. And of course, SS object brings in some LSST specific information about each object. For example, the number of times each object was detected by LSST, or say the absolute magnitude in each of LSST's bands, U, G, R, I, Z, and Y, which are not, orbital elements that you would get from the MPC, but they are things that you would get from LSST observations. So just to illustrate the fact that there's kind of this down select between the MPC orb in DP0.3 and the SS object table in DP0.3, we're again going to run one of these relatively simple count queries, but this time using SS object. And when we do that, we find that indeed there are 4.4 million solar system objects detected in these simulated Rubin observations out of the total of about 14.5 million. So a factor of 3 to 4 down select there. A third really important table that Sarah mentioned previously is the SS source table. So this is a much bigger table even than either of the two we've looked at before. And this is because you can think of this as having essentially like a row per detection of each SS object. And LSST will typically get several hundred detections of any well-detected solar system object in a single visit. So then you might expect that you have several hundred times several million is the size of this table. And indeed, it's about 650 million sources. So now we're going to move on to the main belt a little bit and just show looking at one main belt object in the SS source table. So looking at its detections and then making a plot of those. So we have chosen here somewhat arbitrarily this SS object ID. It's a long integer that we know is a main belt object. And we're going to construct now a query of the SS source table where we specifically have a where clause that says SS object ID must be this one known main belt object. And what we're selecting out here are things like heliocentric X, heliocentric Y, which are Cartesian coordinates within the solar system of this object at the different epochs at which the object was detected in the SS source table. So let's define the query and run it similar to how we've done before. This also casts to a pandas data frame again. You'll see that the job has been completed and there's about 319 rows, which makes sense. We do expect sort of several hundred detections per unique solar system object over the course of the LSST survey in general. So now what we're going to do is we're going to take those results that we just got and make one relatively straightforward plot. The idea here is that the heliocentric X and heliocentric Y coordinates that we just queried out for this one object in all of its SS source detections are like the projection of the orbit into the XY plane of the solar system over time. And so if we plot the heliocentric X versus heliocentric Y, we should expect to see something that's kind of like an ellipse that's traced out by various detections that are non-uniformly sampled in time. And indeed, that's what we see here. We have this kind of ellipse that's irregularly sampled with black dots. Those are each of the LSST detections. And then you have the sun as the gold star. And you can see that indeed, if you look at the X and Y labels, you have, a couple AU in either direction, i.e. this has a semi-major axis that's a little bit over 2 AU, which is well within the main belt range. So now we're just going to make one very last plot here. This is sort of to do a population analysis of the main belt, an initial population analysis. So what we're going to want to do is just make a histogram of the semi-major axes, but remember, semi-major axis is not actually a column here, so we'll need to get some different orbital element columns, as you see here. Not all of them we end up using, but the E and the Q, the perihelion distance, we do use. We're getting this out of the MPC orb table mainly because remember, that's what has the orbital elements. We're joining on SS objects so that we can make this cut that requires at least 50 detections for each object that we want returned. And we're again using this approach of restricting to a range of SS object ID to down select by a large factor so that we don't get an overly large sample size, but we sort of do get a randomly selected statistically useful sample. So that's our query, and then we'll run it. This could take up to, again, several dozen seconds. Then the next thing we're going to do once the query finishes is to, again, cast this to a pandas data frame for ease of use, and we'll print out the number of results that we get. So the very last part of this demo is we're just going to make a plot of a histogram in a 1D histogram of the main belt asteroid semi-major axes to see what that looks like. And there's various possible definitions you can imagine adopting for the main belt, but for this, we're just going to stick with a relatively simple one of the semi-major axis between 1.6 AU and 4.2 AU. Okay, so that query looks like it finished, at least for me. Let's cast to a pandas data frame and see how many real rows we got, about 340,000. So that's a good size sample we can make a histogram out of. So as I mentioned, we're going to make this cut on semi-major axis, but we first need to use the utility function we defined previously to actually calculate that. So here's where we use our custom function we defined, putting in Q, the perihelion distance, and E, the eccentricity, as parameters. So now we have semi-major axes. We're going to define this cut that restricts to the main belt. And then we're going to plot the results, the semi-major axes we computed subject to that cut. And you can see this very nice histogram here, which clearly has some structure in it beyond just being uniform or single modal. And so clearly there's something going on here. And what's going on is that there are the so-called Kirkwood gaps, which arise due to resonances between the asteroid's orbital period and that of Jupiter. Won't go into that in full detail, but if you look at the bottom, there's some references for notebook tutorials that we have in CST where one can explore this in further detail. Okay, so I mean, yeah, I think in the interest of time, maybe we can hold questions to the end after I've done a quick, 10-ish minute portal demo as well. Let me see if I can move my screen a little bit. Maybe someone could share the link to the specific markdown file that has the instructions for the portal demo. That would be helpful. Otherwise, I'll just go through it. But suffice it to say that in this DP1 SciPrep seminars, in this GitHub repo, there's a markdown file that has full instructions you can follow along with for this portal demo. And so I'll go through that now. The way that we do this is we want to go to data.lsst.cloud again, but this time we want to go into portal. And we want to go to DP 0.3 catalogs because that's what we're working with here. That's the solar system data set for that we have currently on RSP. And so the default you see here, it has this 10-year collection again, which is what we want. But this is the sort of user-assisted interface we call it, user interface assisted interface we call it, where you can sort of construct queries visually. What we're going to use actually here is the edit ADQL button in the upper right to actually put in typed out queries that we have. So we're going to make a couple queries. Both of these are of the MPC orb table again. And here's the first one. It's in this markdown file I mentioned previously. This is just selecting a few of the orbital elements out of the MPC orb table, again, with a cut on SS object ID, just to make sure we get a reasonable amount of results, not many, many millions. So let's put that into our ADQ query box, and we're going to put a row limit of at most 200,000 rows. And then we click search. So this may take a few seconds to come up with the search results. And then we'll go on to basically make a custom plot here or manipulate some of the columns a bit. Shouldn't take more than a few seconds. So basically where we're going to go with this is that we're going to make a first plot of semi-major axis and inclination on the would be the two axes, just to see the overall populations in DP 0.3. And then after that, we'll make a couple plots that are more specific to the trans-Neptunian objects. So for that notebook, we're defining that as semi-major axis greater than 30.1 AU, I believe, is what we're adopting. And then from there, we'll make a last plot that's a histogram of diameters in kilometers of the trans-Neptunian objects if we have time. Has anybody's query finished? This seems to be taking a little longer, possibly because we're all trying to run it at the exact same time. We can give this a moment to run, see if it'll finish. Otherwise, I can keep going with a slightly different version here, of an internal version that probably would only be me querying this exact query at this exact time, I would guess. So let me see if we can do that. Okay, let's see if it runs faster here with perhaps fewer people running the same query at the same time. Although if we're running a query of the exact same underlying database, then maybe I'm just adding one more query on top of everything else, in which case that's not helpful. But I guess I can look at the chat and see if anybody's got theirs. Not sure if there's any clear strategy of how to make it go faster. I mean, you could limit the number of rows returned further, but I'm guessing that that's not really the bottleneck, because in the end, it still needs to actually make the query before it decides to sub-select what rows to show you. So
Do you want to switch over to the markdown file and walk them through the results from that?
yeah, sure. Thanks, Tina. If that was Tina, I think it was.
That was.
Yeah. Okay, thanks. So yeah, what we would do, and let me know if things start to finish, but what we would do here is we would arrive first at this screen that has the results, and obviously you can't see all 200,000 results at once, but there's about 175,000 results you can see in total. And then the first thing that we would do is we want objects that are bound to the solar system, so we would start by putting in a constraint on one of the columns to filter things out. So you would put this less than one constraint in on the eccentricity column, which is the leftmost column here. And that would down select a little bit to remove unbound objects. And then furthermore, what we want to do is we want to define a custom column called semi-major axis, because remember, again, the semi-major axis is not natively included in these tables. So you need to calculate it from the combination of perihelion distance q and eccentricity. So to do that, you would go to this rectangle, this vertical rectangle with a plus. That's what you click to add a column. And then you would go here and you would enter the name as lowercase a, the mathematical expression using the column names that we have like q and e, and the units of astronomical units, and description semi-major axis. So then now you have an extra column to work with. And then what we would do from there is create a scatter plot using that extra column. So we would go to, I think you can see it here, but there's a plus mark in the upper left to make a new plot. And then we would define that as, let me just check, as a new scatter plot. And on the x-axis, you would have semi-major axis, and on the y-axis, you would have inclination, just so we can get a sense of what's out there in the solar system. And for the boundaries, we would set it to be 0 to 60 AU on the x-axis and 0 to 80 degrees on the y-axis. And then you would hit OK. And that would pull up this chart. And you can see that indeed there is a semi-major axis on the x-axis and inclination on the y-axis. And we notice generally that there's a lot of stuff at a few AU, i.e. the main belt, but then there is a bunch of stuff as well, those relatively small numbers at large distances greater than 30 AU, large semi-major axes, and that's the trans-Neptunian object populations that we want to focus on for the rest of this tutorial. Still running, so let's keep going in the markdown. Now let's do another query, or we would do another query that has a little bit more specifically drilling down into the TNO population, trans-Neptunian objects. And the way it's doing that is we're again querying basically the same list of columns, although with the MPC-H, the H absolute magnitude included from the MPC orb 10-year table. And we're going to do this cut on semi-major axis, though again, since semi-major axis isn't actually a column, we have a little bit of math here to make this cut. And we're also getting rid of long period comments in this where clause using this does not equals LPC within the MPC designation column. And we're going to keep the row limit at 200,000, although I think this is going to return only about 60,000 objects to begin with. And then the first thing we would do here is make a plot of eccentricity as a function of semi-major axis. So again, where we go to that plus sign at the upper left of the plotting panel to make a new plot, we would define the plot parameters. We would again keep it as a scatter plot. In this case, we wouldn't make a new semi-major axis column, although you could. We would just do the math here in the plot definition. So the x-axis would be the perihelion distance over 1 minus the eccentricity, i.e. the semi-major axis, and the y-axis would be the eccentricity, which is already a column for us. And we would set the x limits to be 30 to 100 AU because we want to focus on the trans-Neptunian objects, and that kind of lines up with the query we ran anyway that restricted to semi-major axes greater than 30.1 AU. So hitting OK on that would then show us the following plot, where you can see there is kind of like this overall trend of semi-major axis versus eccentricity, with some scatter around it. But then you also see that there are these different sort of substructures or subpopulations in the plot. So sort of the takeaway here would be that there are several subpopulations of trans-Neptunian objects, such as the classical resonant, scattered disk, and detached subpopulations. I won't go into explaining that all here since we're already only 7 minutes away from the end of the session. But nevertheless, this is a good illustration of some of the detail aspects of what's really in the trans-Neptunian object populations and what was put into the simulations of DP 0.3. So the last thing that we would be able to do here is to look at something a little bit different, which is to estimate diameters of each of the trans-Neptunian objects from the previous query. And the idea here is that the MPC H absolute magnitude is kind of meant to be a proxy for the size of an object, but to get from the MPC-H to the size in kilometers, you need to make an assumption about albedo. So for the sake of this tutorial, for brevity and simplicity, we're going to assume a fixed albedo value of 0.15, which is commonly adopted. And then once you make that simple assumption about the albedo, it's a relatively simple equation shown here, how you would convert from the MPC-H absolute magnitude into a diameter in kilometers. And you can translate that mathematical function into syntax here that would be useful in order to define a new column. So we would again go to that button in the upper right that has the vertical rectangle with the plus sign on it to create a new column. And in this case, we would call it capital D. We would put in a copy paste of this expression here that defines how you convert from MPC-H to diameter in kilometers, assuming that you have a fixed albedo of 0.15. We would put units as kilometers and description as diameter. And then we would make a new plot by clicking that big plus button in the upper left. And in this case, we would want to change the plot type dropdown from scatter to histogram because we want to make a 1D histogram just to see a log histogram of the diameters. So on the x-axis, you'd have the log 10 of the diameter because there could be a big range here. So we want to do logarithmic. We would change number of bins from 50 to 100. And we would also go down towards the bottom, and under options, we would check on the log box for the y-axis as well, so that we get sort of a log histogram. Then we would hit OK, and the resulting plot would look something like this, where you have log diameter in kilometers on the x-axis, and you have number of objects per bin, logarithmic on the y-axis. And you can see that according to the assumptions we made and the assumptions put into the DP0.3 simulations, this distribution would peak at of order 100 kilometers in size. And you can also see that there's some tails, right, especially towards the small diameter end. And that probably has to do with some things that weren't quite right about the assumptions that were put in either in this notebook or in the simulations themselves about the albedo. It would be my first guess as to why you get some of that tail to the very small values of objects, or very small diameters that likely you wouldn't be able to see to very large distances in the solar system. So with that, I think we can end there and take questions for a few minutes. I think Sarah and I would also be happy to stay a little bit later if questions go beyond the hour, given that we left only a handful of minutes for questions. We were trying to pack a bunch into here. So yeah, thank you everyone for attending, and sorry to delay questions to the end, but we're happy to take some now. All right, well, if there's no questions, I think it's perfectly fine to end a couple minutes early. We did a pretty good job of sticking to time here. So again, thanks everyone for joining. We will get around to, within a few days, posting the recording of this online as well. And the materials are on GitHub, of course, to go through or check out in more detail at any time, including the slides are linked there as well as a reference. So again, thanks everyone for attending, and catch you at the next one of these Rubin Science Assemblies.
Thanks, you too. That was really good.
Thanks, Bob. Great seeing you.
Thanks, everyone.
Thanks.
Thank you.
We don't need to do anything to stop the recording, do we? I don't think so.
You might need to hit stop. I think we do. I can hit it.